The thermal efficiency concept needs refinement, David. Our investors expect more innovative solutions, my business partner said, dismissing my prototype design in front of venture capitalists from Kleiner Perkins. The investors nodded thoughtfully. My partner, Thomas Bradford, smiled confidently and opened his engineering portfolio. Let me show you the breakthrough propulsion system I've been developing for the aerospace application. I sat in the Silicon Valley conference room, watching Thomas present engineering designs that were unmistakably mine. The thermodynamic calculations were mine. The materials specifications were mine. Even the specific mechanical innovations and efficiency improvements came directly from prototypes I'd spent 14 months developing and sharing with him during our partnership meetings. This was the 19th time in 2 years that Thomas had stolen my engineering designs and presented them as his own work to investors, manufacturers, or industry publications. I'd documented every instance meticulously, gathered irrefutable proof, and planned my response with the precision I brought to mechanical systems analysis. Because what neither Thomas nor these venture capitalists knew was that I'd already filed provisional patents on all my engineering innovations, secured manufacturing contracts with 2 major aerospace companies who wanted to work directly with me, and been approached by a leading engineering firm about a senior partner position. I'd also consulted with patent attorneys who confirmed that Thomas had no legal rights to designs I'd created independently. In 96 hours, I would dissolve our engineering partnership and reveal that every innovative system Thomas had been claiming credit for was actually my design work, protected by patents and comprehensive engineering documentation. His company would lose its technical foundation, its major contracts, and its industry credibility. Mine would launch with the innovations he'd tried to steal, proper attribution, and opportunities he'd blocked through his exploitation. Before we witness how a brilliant mechanical engineer whose designs were stolen for years used patent law and industry connections to destroy her partner while launching her own successful firm, I want to thank you for being part of this community. A community that believes engineering theft deserves the same consequences as any other stealing, and that technical plagiarism should be exposed publicly. If you've had your engineering work stolen, if you've watched partners take credit for your designs, if you've been the invisible technical force behind someone else's company success, this story will resonate deeply. Hit that subscribe button to join thousands who appreciate stories where documentation and strategic planning overcome exploitation in technical industries. Now let's step into the world of mechanical engineering, where a talented designer's work was systematically stolen by her charismatic business partner, where industry relationships enabled exploitation, and where 2 years of careful preparation created the foundation for complete professional destruction and technical triumph. My name is David Chen, and I'm a 33-year-old mechanical engineer originally from San Jose, California. I grew up in a family where both my parents worked in semiconductor manufacturing, and I was surrounded by discussions about precision engineering, materials science, and the intersection of theory and practical application. Mechanical design felt like my natural language from childhood. I learned to read technical drawings when I was 11 years old, sitting at my father's workbench while he worked on manufacturing process improvements. He taught me about tolerances, about how mechanical systems needed to balance theoretical efficiency with manufacturing constraints, about the responsibility engineers had to create solutions that worked reliably in real-world conditions. Those lessons shaped everything about how I approach design. My father worked as a manufacturing engineer at a semiconductor equipment company, designing automated handling systems for silicon wafers. He'd bring home broken components and challenge me to figure out why they'd failed. We'd examine wear patterns, discuss material properties, analyze stress concentrations. He taught me that understanding failure mechanisms was essential to creating robust designs. I remember one specific project when I was 13, helping my father redesign a robotic gripper that kept dropping expensive wafers. We analyzed the pneumatic actuator system, identified that pressure fluctuations were causing grip force variations, and developed a feedback control modification that solved the problem. Seeing that analytical thinking could prevent costly failures was profoundly influential. My mother contributed a different perspective to my engineering education. As a materials scientist specializing in thermal management, she taught me about how material properties determined what was mechanically possible. She'd explain thermal conductivity, coefficient of thermal expansion, how materials responded to temperature cycling. I learned that innovative mechanical design required deep understanding of materials science. During high school, I participated in robotics competitions and engineering challenges. I designed mechanical systems for our school's first robotics team, developing innovative solutions for manipulating game pieces and navigating obstacles. Our team won regional championships 2 years running, largely due to mechanical designs I'd developed that were more efficient and reliable than competitor approaches. I earned a full scholarship to MIT, studying mechanical engineering with a focus on thermodynamics and advanced propulsion systems. College was intellectually thrilling, learning from professors who were pushing boundaries of what mechanical engineering could accomplish in aerospace and energy applications. I was particularly interested in how innovative thermal management could improve efficiency in propulsion systems. My sophomore year professor, Dr. Sarah Mitchell, had worked on jet engine development at Pratt & Whitney and brought that experience to her teaching. She pushed us to think about practical constraints alongside theoretical optimization, to understand manufacturing realities, to design systems that could be maintained and serviced. Her mentorship profoundly influenced my engineering philosophy. During junior year, I joined MIT's Rocket Propulsion Lab and worked on developing more efficient combustion chamber cooling systems. Traditional rocket engines faced significant thermal management challenges that limited performance and reliability. The extreme heat from combustion, often exceeding 3,000 degrees Celsius, had to be removed continuously to prevent structural failure. Conventional cooling approaches used regenerative cooling where propellant flowed through channels around the combustion chamber before injection, but these systems faced limitations. I became fascinated by the fundamental challenge of managing such intense heat flux in the harsh environment of rocket combustion. I spent months studying historical rocket engine designs, analyzing thermal failures, understanding the physics of high-temperature heat transfer. I worked closely with Dr. Mitchell and graduate students developing next-generation propulsion concepts. My design used a novel flow pattern geometry that enhanced heat transfer while minimizing pressure drop. Traditional regenerative cooling channels used simple axial or helical patterns that were effective but not optimized for the actual heat flux distribution in combustion chambers. I developed a computational approach to optimize channel geometry based on predicted thermal loads. The approach required careful analysis of fluid dynamics, heat transfer, and structural mechanics. I created detailed computational fluid dynamics models of coolant flow through the channels. I coupled those with finite element thermal stress analysis to ensure the structure could withstand the thermal and pressure loads. I validated the models with experimental testing on subscale combustors. The optimized cooling design showed 15% better heat removal with lower pressure drop compared to conventional approaches. This meant engines could operate at higher chamber pressures, improving performance, or could use lighter structures for the same operating conditions. The innovation had practical applications for commercial and military propulsion systems. I documented the entire development process in detailed technical reports. I photographed prototype components during fabrication and testing. I kept engineering notebooks with dated entries describing design decisions and test results. This documentation discipline, learned early in my career, would prove crucial years later when protecting my intellectual property. The research resulted in a paper that won Best Student Publication at the AIAA Propulsion Conference. The recognition caught attention of several aerospace companies recruiting at MIT. Pratt & Whitney, SpaceX, and Aerojet Rocketdyne all expressed interest in my work. More importantly, the project demonstrated my ability to develop genuinely innovative solutions to complex thermal and mechanical challenges. My senior thesis involved designing a compact heat exchanger for electric vehicle battery thermal management. The challenge was significant because battery performance and safety depended critically on maintaining optimal temperature ranges, typically between 20 and 30 degrees Celsius. Too cold and the batteries couldn't deliver full power. Too hot and they degraded rapidly or could become unsafe. Conventional battery cooling systems used either air cooling or liquid cooling with cold plates. Air cooling was simple but had limited heat removal capability and created temperature non-uniformities. Traditional liquid cold plates were effective but added significant weight and complexity. I wanted to develop a solution that achieved liquid cooling performance in a lighter, more compact package. I designed a microchannel heat exchanger using additive manufacturing techniques that weren't yet common in automotive applications. The design featured channel dimensions of less than 1 mm, creating enormous surface area for heat transfer in minimal volume. The microchannels were arranged in patterns optimized for flow distribution and minimal pressure drop. The challenge was that microchannel heat exchangers typically required precision machining that was expensive at automotive production volumes. Additive manufacturing, specifically selective laser melting of aluminum alloys, could create the complex internal geometries economically. The approach required careful consideration of printable geometries, surface finish effects on heat transfer, and structural integrity of printed parts. I developed the complete heat exchanger design including thermal analysis, fluid flow modeling, structural validation, and manufacturing process specifications. I worked with MIT's Additive Manufacturing Lab to fabricate prototypes. I built a test rig to measure thermal performance under conditions simulating electric vehicle battery cooling requirements. The prototype heat exchangers demonstrated exceptional performance. They achieved 20% better heat transfer per unit mass compared to conventional automotive cold plates. The compact design enabled tighter integration with battery modules. The additive manufacturing process proved viable for automotive production volumes with appropriate quality controls. The thesis earned departmental honors and was featured in engineering publications as an example of how advanced manufacturing could enable innovative thermal solutions. Several automotive companies expressed interest in the technology. Tesla recruited me specifically based on that thesis work, and my first project there involved further developing the concept for production applications. After graduation, I joined Tesla's thermal systems engineering team, working my way from junior engineer to senior design engineer over 6 years. The experience taught me about the challenges of automotive scale engineering, about balancing performance with cost and manufacturability, about coordinating across design, manufacturing, and testing teams. My first major project at Tesla was improving the Model S battery cooling system to support faster charging rates. Higher charging power generated more heat that needed to be removed to protect battery life and safety. I developed an enhanced coolant flow distribution system that improved cooling uniformity while using existing hardware with minimal modifications. The design required detailed thermal and fluid analysis to optimize flow patterns. I created computational models of the battery pack thermal behavior, validated them against test data, and iterated the design to maximize cooling performance. The improved system enabled 20% faster charging while maintaining battery temperature limits. The project demonstrated my ability to develop practical solutions to complex thermal challenges within the constraints of existing production systems. Tesla filed patents on the cooling system innovations, with my name as primary inventor. The experience taught me about intellectual property protection in engineering contexts, lessons that would prove crucial years later. I worked on numerous advanced projects during those 6 years, developing thermal management solutions that became signature elements of Tesla's engineering portfolio. An innovative cold weather battery preheating system that improved winter range. A lightweight heat exchanger design for the Model 3 that reduced cost while maintaining performance. A thermal management approach for the Powerwall battery storage system that enabled more compact packaging. One project I'm particularly proud of involved developing a direct liquid cooling system for electric motors that enabled higher power density. Traditional electric motor cooling used either air cooling or indirect liquid cooling where coolant flowed through a jacket around the motor housing. Both approaches had fundamental limitations in heat removal capability that constrained how much power could be extracted from a given motor size. Air cooling was simple and reliable but had limited heat transfer capability. Electric motors are fundamentally limited by temperature of their windings and magnets. Permanent magnet motors, which Tesla used for their efficiency, had magnets that lost strength if they got too hot. The copper windings could handle high temperatures but had increased electrical resistance when hot, reducing efficiency. Effective cooling allowed higher power output from the same motor size. Indirect liquid cooling was better than air but still had significant thermal resistance between the heat-generating components and the cooling fluid. The coolant had to transfer heat through the motor housing wall, which created a bottleneck. I wanted to develop a direct cooling approach where coolant contacted the hot components more directly. The concept was to circulate cooling fluid directly through passages integrated into the motor housing, bringing coolant much closer to the heat sources. The challenge was significant because the cooling fluid needed to be electrically non-conductive to avoid creating electrical shorts in the motor. The fluid also needed excellent thermal properties, chemical stability, and compatibility with motor materials. I researched dielectric cooling fluids used in electronics applications and identified candidates that could work for motor cooling. I developed housing designs that integrated cooling passages directly adjacent to the stator windings where most heat was generated. The design required sophisticated flow analysis to ensure good coolant distribution and heat removal without excessive pressure drop. The passages were designed with turbulence promoters to enhance heat transfer. I optimized the geometry using computational fluid dynamics to balance heat removal against pumping power requirements. I designed sealing systems to prevent coolant leakage while allowing for thermal expansion. I validated the designs with prototype motors tested across the full power and speed range. The direct liquid cooling system enabled 30% power density improvement compared to conventional air-cooled motors. This meant Tesla could use smaller, lighter motors without sacrificing performance. A smaller motor meant more interior space or larger battery pack in the same vehicle package. The weight savings improved vehicle efficiency and performance. The company filed multiple patents on the technology with me as primary inventor. The patents covered the cooling passage geometry, the sealing concepts, the fluid selection criteria, and the integration with motor electromagnetic design. These were my first patents as primary inventor, and the experience taught me about patent documentation and intellectual property protection. The success of the motor cooling project established my reputation internally as someone who could develop breakthrough solutions to difficult thermal and mechanical challenges. Senior leadership began assigning me the most difficult thermal problems, the projects where conventional approaches had failed and we needed innovative solutions to enable new product capabilities. One such project involved developing a thermal management system for the Model S battery pack during supercharger fast charging. The standard charging thermal system worked well for normal charging rates, but Tesla wanted to dramatically increase charging speeds to reduce charge times for long-distance travel. Higher charging power meant much more heat generation in the battery cells that had to be removed to protect battery life and safety. The challenge was to improve cooling performance using the existing battery pack architecture with minimal modifications. Redesigning the entire pack wasn't viable for production timing reasons. I needed to work within tight constraints while achieving significant performance improvement. This kind of constrained optimization became a signature of my engineering approach. I analyzed the existing coolant flow distribution through the battery pack and identified that flow was poorly distributed between different battery modules. Some modules received more cooling than needed while others were undercooled. By redesigning the coolant manifolds and flow routing, I could improve distribution without changing the basic pack architecture. I created detailed computational models of the complete battery thermal system including coolant flow, heat transfer, and individual cell temperature prediction. I validated the models against extensive testing data. I used the validated models to optimize the flow distribution system, testing hundreds of design variations to find the best solution within the manufacturing constraints. The improved cooling system enabled 20% faster charging while maintaining battery temperature limits. This translated directly to reduced charging time for customers, a major competitive advantage for Tesla. The project demonstrated that sometimes the most impactful innovations came from deeply understanding existing systems and optimizing them rather than always pursuing completely new approaches. By my 5th year at Tesla, I'd become known as a technical leader who could solve problems that stumped other engineers. Senior leadership would assign me projects where conventional approaches had failed, where we needed innovative solutions to enable new product capabilities. I was proud of these contributions, though frustrated by working within someone else's company structure where individual recognition was limited. I wanted to pursue my own vision for advanced thermal and propulsion systems, to develop technologies that could be applied across multiple industries rather than focusing solely on electric vehicles. I wanted my own engineering firm where I could fully express my technical capabilities without filtering through corporate priorities and organizational hierarchies. At 30, I decided to start my own engineering consulting firm. I had strong technical skills, proven track record of innovative designs, and enough industry connections to make independence feasible. What I didn't have was business development capabilities, established manufacturing relationships, or the operational infrastructure that engineering firms needed to secure major contracts. I met Thomas Bradford at an aerospace engineering conference in Seattle. He was 42, charismatic and well-connected, with an MBA from Stanford and 2 decades of experience in business development and engineering program management. He approached me after my presentation about advanced thermal management systems, saying he'd been looking for a talented engineer partner to build a firm focused on innovative propulsion and thermal technologies. We met for coffee the following week at a cafe near downtown San Jose. Thomas talked enthusiastically about his vision for an engineering firm that could develop breakthrough technologies for aerospace, automotive, and energy applications. He said the market had strong demand for innovative thermal and mechanical solutions, but that most firms either focused narrowly on single applications or lacked the technical depth to develop genuinely novel approaches. Thomas explained his background in program management had taught him how aerospace and automotive companies made technology sourcing decisions. He understood their procurement processes, technical requirements, financial structures that made consulting firms attractive to large manufacturers. He knew how to position engineering services to appeal to program managers willing to pay premium rates for innovative solutions. He said this business acumen combined with my technical capabilities would create something unique. Over several meetings, Thomas outlined how a partnership might work. He'd handle all business development, client acquisition, contract negotiation, and firm operations. I'd focus entirely on engineering, working with clients on technical solutions and managing the design aspects of projects. The division seemed perfect, allowing me to concentrate on engineering while someone else handled aspects of business I found less engaging. Thomas had connections to engineering directors at major aerospace and automotive companies, understood the business side of technical consulting, and could handle everything from client acquisition to financial management. He said my engineering talent combined with his business expertise would create a formidable partnership. The division of responsibilities seemed ideal. We formed Bradford Chen Engineering as a 50-50 partnership, both our names on the LLC documents. Thomas handled initial business development while I focused on building our technical capabilities and engineering service offerings. We secured office space in Sunnyvale with laboratory equipment and workbenches that would impress potential clients. The setup felt professional and promising. The office featured a combination of engineering workspace and client presentation areas. Thomas insisted on sophisticated CAD workstations, rapid prototyping equipment, and testing capabilities that would demonstrate our technical capabilities. We installed large monitors for presenting engineering analyses, whiteboards for technical discussions, and a small machine shop for prototype development. Thomas hired a project manager and administrative coordinator, bringing professional structure to the firm's operations. He designed branding and marketing materials with technical aesthetic. He set up the business infrastructure, established banking relationships, negotiated equipment leases, created project management systems. The operational foundation appeared solid and professional. The early months were productive. I developed engineering service offerings for different technical domains we wanted to pursue, creating a portfolio that showcased our firm's capabilities in thermal management, propulsion systems, and mechanical design. Thomas would review designs and provide feedback, always enthusiastic about the work I was producing. He'd bring potential clients to the office to see my engineering work, presenting it as examples of what we could deliver. I created comprehensive technical proposals for various engineering challenges that demonstrated our capabilities across different applications. An innovative rocket engine cooling system for small satellite launchers that used additive manufacturing to achieve performance previously requiring much larger engines. A compact heat exchanger design for hybrid aircraft propulsion that integrated with turbine engines to improve efficiency. A thermal management solution for high-power military electronics that could operate in extreme environments. An advanced battery cooling system for electric aircraft that enabled higher energy density. Each proposal represented weeks of engineering analysis and design work. The rocket engine cooling system proposal included detailed thermal analysis showing heat flux distributions, structural calculations proving the design could withstand combustion pressures and thermal loads, and manufacturing specifications for the additive manufacturing process. I created cross-sectional views showing the intricate internal cooling passages, performance predictions across different operating conditions, and comparison with conventional approaches. The hybrid aircraft heat exchanger proposal addressed the specific challenge of integrating thermal management with existing turbine engine architectures. Aircraft engines operated across wide ranges of temperature and pressure, and any added components had to be extremely lightweight and reliable. I designed a heat exchanger that recovered waste heat from turbine exhaust to preheat inlet air, improving thermodynamic efficiency without adding significant weight or complexity. The military electronics cooling proposal tackled the problem of removing high heat flux from compact electronics packages that might operate in desert heat or Arctic cold. Military systems couldn't rely on active cooling with moving parts that could fail. I developed passive cooling approaches using advanced heat pipes and phase change materials that could maintain electronics within operating temperature across extreme ambient conditions. The electric aircraft battery cooling system represented perhaps the most challenging proposal because aircraft weight constraints were so severe. Every kilogram of cooling system reduced payload or range. I designed an ultra-lightweight cooling approach using micro-channel cold plates integrated directly into battery module structure, functioning as both cooling and structural elements. The dual-function design minimized added weight while providing excellent thermal performance. I shared everything with Thomas during this development phase, walking him through my engineering analysis, explaining the thermodynamic principles and mechanical design decisions behind each approach. I thought we were partners building a firm together, that my openness about technical decisions was normal collaboration between engineering and business leadership. I had no indication yet that Thomas was planning to claim this work as his own. Thomas would ask technical questions during these reviews, showing genuine interest in understanding the engineering work. He'd inquire about why I'd chosen specific materials for high-temperature applications, how I'd approached thermal analysis for transient versus steady-state conditions, what informed my decisions about manufacturing methods and tolerances for different production volumes. He'd take notes during our discussions, which I interpreted as a business partner learning enough about engineering to effectively represent our firm to clients. I appreciated his engagement, thinking it showed respect for the technical work and desire to understand what our firm offered. I didn't realize he was documenting my engineering approaches to later present them as his own innovations. We'd have weekly partnership meetings where I'd update Thomas on engineering work progress and he'd share business development activities. I'd show him latest analysis results, prototype developments, client technical deliverables. He'd describe meetings with potential clients, contract negotiations, administrative matters. The meetings felt like productive partnership collaboration. During one early partnership meeting, Thomas asked me to prepare a technical presentation he could give to a potential aerospace client while I was traveling for a conference. He said the client couldn't meet when I was available, but the opportunity was too good to delay. He wanted to present our rocket propulsion capabilities using the cooling system work I'd developed. I prepared a comprehensive technical presentation showing the cooling system design, thermal analysis results, and performance advantages. I wrote detailed speaker notes explaining the engineering concepts so Thomas could present the material effectively even without deep technical understanding. I thought this was normal partnership support, helping my business partner represent our technical capabilities. Thomas gave that presentation and returned with an expression of interest from the aerospace company. He seemed pleased with how it had gone, saying the client was impressed with the innovative approach. But in describing the meeting, he mentioned they'd been particularly interested in his engineering background and his thermal analysis methodology. I felt slightly uncomfortable but told myself he'd probably just used inclusive language about the firm's capabilities. That presentation marked the beginning of a subtle pattern I didn't fully recognize at the time. Thomas began scheduling more client meetings without me present, saying he could handle preliminary discussions and bring me in for detailed technical work once clients were seriously interested. He'd present my engineering work in these meetings, returning with potential contracts and positive client feedback. I rationalized this division of labor as appropriate specialization. Thomas handled business development and I focused on engineering. It seemed efficient for him to do initial client meetings while I concentrated on technical work. I didn't understand yet that he was presenting my innovations as his own technical expertise during these meetings. The office environment Thomas created also contributed to an imbalance I didn't initially recognize. He positioned his desk prominently in the office, visible to anyone entering. My engineering workspace was in a back area with the CAD stations and prototyping equipment. When potential clients visited the office, they'd first encounter Thomas in his business principal role before seeing the engineering spaces where I worked. Thomas would give office tours to visitors, showing them our capabilities while describing the work in ways that subtly claimed technical leadership. He'd say, "We developed this approach," while standing in front of my engineering workstation showing my CAD models. He'd describe our technical philosophy, while presenting prototypes I'd designed and built. The language was ambiguous enough that I didn't object at the time. He also began representing our firm at industry conferences and networking events. He'd attend without me, saying someone needed to maintain engineering work progress while he did business development. He'd give presentations about our firm's capabilities using slides I'd created showing my technical work. I'd hear secondhand from people I knew in the industry that they'd seen Thomas present interesting propulsion innovations, not realizing these were my designs being presented as his work. The pattern escalated so gradually that I didn't recognize the systematic nature of what was happening. Each individual instance seemed explainable. Thomas was doing business development using our firm's technical capabilities. Partners in engineering firms used inclusive language. Division of labor meant he handled client-facing activities while I focused on engineering. But the cumulative effect was that industry professionals increasingly associated our firm's technical innovations with Thomas rather than me. The theft started subtly during client presentations. Thomas would describe designs using language that subtly claimed technical credit. He'd say, "We developed," or "our innovation," when discussing work I'd created entirely on my own. He'd present engineering analyses without clearly stating that I'd performed all the technical work. At first, I told myself this was normal business communication, that Thomas was using inclusive language to present us as a unified firm. But the pattern became troubling when he started taking technical meetings without inviting me, returning with signed contracts for projects where clients thought Thomas was the lead engineer. The first undeniable instance involved a propulsion system development project for a small satellite launcher company. The client needed an innovative rocket engine cooling system that could handle high heat fluxes in a compact, lightweight package. Traditional regenerative cooling approaches were too heavy and complex for their small launcher application. I spent 4 months developing the solution. I analyzed heat transfer requirements, evaluated advanced manufacturing methods, modeled thermal and structural performance. The resulting design used additive manufacturing to create intricate internal cooling passages that achieved exceptional heat removal in minimal volume and mass. The cooling system design featured a novel geometry that optimized coolant flow distribution while minimizing pressure drop. The approach required sophisticated analysis of conjugate heat transfer, structural mechanics under thermal loading, and manufacturing constraints for additive processes. I created detailed engineering models, validated them with experimental testing, and developed comprehensive documentation. I documented every aspect of the design, including thermal analysis results, structural calculations, materials selection rationale, manufacturing process specifications, and performance predictions. The complete engineering package represented months of intensive technical work and innovation. Thomas attended the presentation meeting with me, positioned as firm principal while I was introduced as chief engineer. During the presentation, I walked through the technical approach, explaining the thermodynamic analysis and design optimization. The client asked sophisticated questions about the cooling system performance, and I provided detailed answers demonstrating deep understanding of the physics and engineering. After the presentation, the client told us they were impressed with the design and wanted to proceed with a development contract. They mentioned being particularly excited about Thomas's innovative approach to regenerative cooling, and his understanding of additive manufacturing applications. I realized Thomas had positioned himself as the engineering mind behind the design during pre-meeting conversations I hadn't been part of. 2 weeks later, Thomas showed me the signed contract. The client had committed to a substantial development program with multiple milestones and testing phases. Thomas seemed pleased with the deal, saying the satellite launcher project would be perfect for establishing our firm's reputation for innovative propulsion engineering. But as he described the contract negotiation, I understood he'd claimed my technical work as his engineering vision. The theft escalated from there. Thomas began scheduling client meetings without including me, presenting my engineering designs as his own technical innovations. He'd return with signed contracts and tell me about projects he'd won using technologies I'd developed. He was performing engineering expertise he didn't actually possess, using my work to create an illusion of technical leadership. I started noticing patterns in how Thomas described our firm to prospective clients and in industry contexts. He'd talk about his approach to thermal optimization and his innovations in propulsion cooling when discussing designs I'd created entirely independently. He was building his professional reputation on my intellectual property while keeping me invisible. During one particularly frustrating presentation, Thomas used engineering analyses I'd created alongside a presentation describing his design philosophy and his innovative framework for thermal mechanical optimization. Every design showed work I'd developed, every technical insight came from my engineering, every innovation reflected my technical thinking. But Thomas spoke about it all as if these approaches originated with him. I confronted Thomas after that presentation about claiming my engineering work as his technical vision. He looked at me with apparent confusion, as if my frustration was incomprehensible. He said that as partners in an engineering firm, all designs were ours, regardless of who physically created them. He said I was being territorial about work that belonged to the partnership we'd built together. The conversation became an argument about ownership, attribution, and what partnership meant in technical professional contexts. Thomas insisted his business development and client relationships were equally valuable to my engineering work, that the firm's success was collaborative even if I'd physically created all the designs. He said demanding individual credit undermined our partnership and made me seem difficult to work with. I left that conversation feeling manipulated and diminished. Thomas had taken a legitimate complaint about intellectual property theft and reframed it as my personal problem with sharing recognition. He'd made me question whether I was being unreasonable to expect acknowledgement for creating every design our firm had produced. That evening, I called my former MIT advisor, Professor Sarah Mitchell. I described what was happening with Thomas. She listened carefully, then told me something that changed my entire understanding of the situation. She said she'd seen this pattern before in engineering firms, business partners systematically claiming credit from talented engineers, keeping them invisible while building reputations on stolen technical work. Professor Mitchell emphasized that engineering designs and technical innovations were protected under patent law and intellectual property rights. She explained that I could file patents on my innovations, document my engineering development process, and establish legal proof of inventorship. Most importantly, she said comprehensive documentation would be crucial if I needed to leave the partnership and protect my work. She recommended I immediately start protecting my work legally and documenting that all designs were mine. She suggested consulting with patent attorneys, filing provisional patents on all my innovations, keeping detailed engineering notebooks with dated entries, and building relationships with clients independent of Bradford Chen Engineering so I'd have professional options if I needed to leave the partnership. Following Professor Mitchell's advice, I began systematically documenting my work and protecting my intellectual property. I started keeping detailed engineering notebooks describing my design process for every project, with dated entries and witness signatures. I photographed prototype development work, saved all computational models with metadata showing creation dates, documented experimental test procedures and results. I also began filing provisional patent applications on all my engineering innovations. Provisional patents provided 1 year of patent pending protection while I developed full patent applications. I filed provisionals on the rocket engine cooling system, the heat exchanger designs, the thermal management innovations. Each filing established legal record of my inventorship with detailed technical disclosures. The patent filing process required comprehensive documentation of the inventive concepts, how they differed from prior art, and detailed engineering descriptions. I worked with a patent attorney to prepare thorough disclosures that would withstand examination. Each provisional application created legal protection for my innovations and proof that I was the inventor. I also started registering copyrights on technical documentation, engineering reports, and analysis methodologies I'd developed. While the underlying engineering concepts couldn't be copyrighted, the specific expression of those concepts in technical documents could be protected. This created additional legal protection for my work. Simultaneously, I began building professional relationships independent of Thomas and Bradford Chen Engineering. I attended technical conferences alone, joined professional engineering societies, made sure people in the aerospace and automotive engineering communities knew me as an actual engineer rather than just Thomas's business partner. I was establishing my own professional identity. One particularly valuable connection came through an ASME Women in Engineering network I joined. Through this group, I met several successful women engineering firm owners who'd faced similar credit theft earlier in their careers. They shared strategies for protecting work, advice about leaving exploitative partnerships, and encouragement that my concerns about Thomas's behavior were legitimate and serious. One engineer, Dr. Maria Rodriguez, told me she'd left a partnership 9 years earlier after her partner had systematically claimed credit for her technical innovations. She'd struggled initially after leaving but had built a successful independent consulting practice. She emphasized the importance of having patents filed and comprehensive engineering documentation before confronting exploitation or dissolving partnerships. Maria's story gave me both validation and strategic direction. I wasn't overreacting to Thomas's behavior. I was recognizing a serious pattern of professional theft that required careful response. The documentation I was gathering wasn't paranoid but necessary protection of my intellectual property and technical work. During this documentation period, I also started having careful conversations with clients we'd worked with through Bradford Chen Engineering. I wanted to understand whether they knew I'd created the engineering designs Thomas had been presenting as his work. The conversations were revealing and disturbing. Multiple clients told me they'd assumed Thomas was the lead engineer because of how he'd presented himself in initial meetings and ongoing project communications. They'd believed they were hiring Bradford Chen Engineering primarily for Thomas's technical expertise. Several expressed surprise when I explained I'd actually developed their projects, saying Thomas had certainly implied the designs were his engineering innovations. One client, the chief engineer of an aerospace company we'd done propulsion work for, was particularly direct. He told me he'd contracted with Bradford Chen Engineering specifically because he was impressed with Thomas's presentation about advanced cooling technologies. He'd assumed the technical innovations Thomas showed were Thomas's own engineering work. When I showed him my engineering notebooks and patent filings proving I'd created everything, he was shocked and concerned. The chief engineer said he felt misled, that he'd signed contracts believing he was getting Thomas's engineering expertise when in reality Thomas had no technical capabilities. He told me explicitly that if I left Bradford Chen Engineering and started my own firm, he'd want to work with me directly on future projects. He said several other engineering managers he knew would likely feel the same way. These conversations confirmed that Thomas's credit theft wasn't just affecting my relationship with him but was damaging my professional reputation in ways that would impact my career long-term. Industry professionals thought he was the technical talent behind our firm when in reality he couldn't design a mechanical system if his career depended on it. I also discovered that Thomas had been filing patent applications on my engineering innovations with himself listed as sole inventor or primary inventor with me as contributor. 3 patents on technologies I'd developed had been filed under Thomas's name. The patent applications used my technical disclosures but listed Thomas Bradford as the inventive mind. The first patent was on the rocket engine cooling system, filed as Thomas Bradford primary inventor with David Chen as contributing engineer. The patent described innovations I'd developed entirely independently, with technical details taken from my engineering documentation. Thomas had no technical understanding of the invention but had appropriated it by filing the patent application in his name. The second patent was on an advanced heat exchanger design I'd developed for electric aircraft. Again, Thomas was listed as primary inventor despite having contributed nothing to the technical development. The patent examiner would see Thomas's name first and assume he was the engineering mind behind the innovation. The third patent was on a thermal management system for high-power electronics that I designed from fundamental principles through detailed implementation. Thomas had filed it under his name using my engineering documentation as the technical basis. My name appeared as a contributor but Thomas claimed primary inventorship. The patent fraud was particularly serious because patent law required truthful declaration of inventorship. Thomas had committed legal fraud by falsely claiming to be the inventor of technologies he hadn't created. Beyond the ethical breach, the fraudulent inventorship could invalidate the patents entirely if discovered. I consulted with my patent attorney about the fraudulent patent filings. She confirmed that Thomas had committed inventorship fraud, which was both grounds for correcting the patents and potentially basis for legal action. She recommended documenting the fraudulent filings as additional evidence of Thomas's systematic theft of my technical work. I started reaching out to the clients and companies who'd contracted for my engineering work, explaining that I'd created the technologies they'd hired Bradford Chen Engineering to develop. I asked if they'd be interested in working with me directly if I left the partnership and started my own firm. The response was overwhelmingly positive. Multiple engineering managers said they'd absolutely work with me independently, that they'd been impressed with the technical work and would follow the actual engineer rather than the business partner. One major aerospace company's propulsion director told me explicitly that he'd only contracted with Bradford Chen Engineering because of my capabilities, that Thomas's contribution seemed primarily administrative. I also received an unexpected contact from Jennifer Walsh, Vice President of Engineering at Aerojet Rocketdyne. Jennifer had seen my technical presentations at conferences and been impressed with the engineering attributed to Bradford Chen Engineering. She'd done some research and discovered that I'd actually created those innovations, and she wanted to discuss potential opportunities. Jennifer and I met for lunch near their Sacramento facility. She was direct and professional, saying Aerojet Rocketdyne was expanding their advanced propulsion development group and looking for senior engineers with proven innovation capabilities. She'd reviewed my work and thought my technical approach would align well with their development programs. The offer Jennifer eventually made was compelling. I'd join Aerojet Rocketdyne as principal engineer with path to technical fellow level, leading advanced cooling system development for next-generation rocket engines. I'd have significant technical autonomy, proper attribution for my work as named inventor on patents, and compensation that reflected my actual contributions. But more tempting than joining another company was the possibility of finally starting my own independent engineering firm with the client relationships and intellectual property protection I'd been building. Several companies had committed to working with me directly. I had provisional patents on my innovations. I had comprehensive engineering documentation. The foundation for independence was stronger than I'd initially realized. I consulted with both my patent attorney and an attorney specializing in engineering partnerships. They reviewed all my documentation, including provisional patents, engineering notebooks, and evidence of Thomas's theft. They confirmed that I had strong legal grounds to dissolve the partnership and establish that Thomas had no rights to technologies I'd invented. The attorneys explained that patent law required truthful inventorship declaration. I was the sole inventor of the technologies Thomas had been claiming as his work. His fraudulent patent filings and misrepresentation to clients constituted serious legal violations. I had comprehensive grounds for correcting the patents, dissolving the partnership, and potentially pursuing fraud claims. The documentation I'd gathered was comprehensive enough that they felt confident I could dissolve the partnership cleanly, retain rights to all my technical work, correct the fraudulent patents, and establish my own firm without legal complications. They recommended giving formal notice to Thomas, clearly stating that I was leaving the partnership, retaining all intellectual property rights, and would be correcting the fraudulent patent filings. During the 2 years I spent documenting Thomas's theft and building my exit strategy, the exploitation continued and escalated. Thomas became increasingly brazen about claiming credit, seemingly confident that I wouldn't challenge him. Each instance of theft added to the evidence I was gathering while strengthening my resolve to leave. One particularly egregious example involved a contract with a major automotive manufacturer developing electric powertrains. They needed innovative thermal management for high power density motors and inverters. The technical challenge was significant because power electronics generated intense heat in compact spaces, and conventional cooling approaches limited performance. I spent 6 months developing the thermal management system. I analyzed heat generation patterns, modeled coolant flow and heat transfer, designed innovative cold plate geometries using computational optimization. The resulting design achieved exceptional cooling performance in minimal space, enabling higher power density than competing approaches. The technical solution used microchannel cold plates with optimized flow distribution and advanced manufacturing methods. The design required solving complex conjugate heat transfer problems, structural analysis under thermal stress, and integration with existing automotive manufacturing processes. I created comprehensive engineering documentation including analysis results, prototype test data, and manufacturing specifications. Thomas presented this work to the automotive manufacturer's engineering leadership as his technical innovation. He gave a detailed presentation describing his understanding of power electronics cooling challenges, his approach to thermal optimization, his framework for integrating advanced manufacturing. Every technical insight he described came from my engineering work, but he presented it all as if these innovations originated with him. The client was impressed and signed a multi-million-dollar development contract based on Thomas's presentation. They sent congratulatory emails addressed to Thomas, praising his engineering vision and technical capabilities. They had no idea I'd created everything Thomas had shown them. Thomas forwarded me the emails with a message saying the automotive contract was a great win for our firm. After 2 years of careful preparation, I had everything I needed to leave the partnership and expose Thomas's theft. I had provisional patents on all my innovations establishing my inventorship. I had comprehensive engineering notebooks with dated, witnessed entries. I had commitments from multiple companies to work with me independently. I had legal advice confirming my rights. I had job offers providing backup options. I scheduled a meeting with Thomas at our office on a Wednesday afternoon. I'd prepared everything carefully, consulting with my attorneys about exactly how to handle the dissolution conversation. I had formal written notice of partnership dissolution. I had documentation proving my inventorship of all technologies. I had copies of evidence showing his systematic theft and fraudulent patent filings. Thomas seemed relaxed when I arrived at the conference room, probably assuming this was a routine project review. He had his laptop open, showing an engineering presentation he'd prepared for a potential client pitch later that week. The presentation, predictably, featured my technical work presented as his innovations. I sat down across from him and placed a folder on the table. The folder contained copies of provisional patent filings on every major technology Bradford Chen Engineering had developed, all listing me as sole inventor with comprehensive technical disclosures. It contained engineering notebook entries documenting my development process. It contained evidence of 19 instances where Thomas had claimed my work as his own, including the fraudulent patent filings. I began speaking before Thomas could start his typical meeting routine. I told him I was dissolving our partnership effective immediately. The words came out calmly and clearly. Thomas's expression shifted from casual friendliness to confusion as he began processing what I'd said. "What are you talking about, David?" Thomas asked, closing his laptop. "Dissolve the partnership? If something's bothering you, we can discuss it. We've built something valuable here together." I explained that I held intellectual property rights to every technology Bradford Chen Engineering had developed because I'd invented them independently and filed proper patent applications. I told him I'd documented his systematic misrepresentation of inventorship and had legal counsel confirming his behavior constituted fraud, including false inventor declarations on patent applications. I pushed the folder across the table toward him. Thomas opened the folder and began reviewing the contents. I watched his expression shift as he saw page after page of provisional patent filings, all listing me as inventor, all dated over the past 2 years. He saw the engineering notebook documentation. He saw evidence of his fraudulent patent filings and credit theft. He saw letters from companies stating they'd work with me directly. "This is ridiculous," Thomas said, but his voice had lost its usual confidence. "These are company technologies. Everything we've developed has been collaborative, part of building this business together. You can't just claim ownership of work that belongs to Bradford Chen Engineering." I told him that patent law didn't work that way. I'd consulted with patent attorneys specializing in engineering intellectual property. Inventorship belonged to the person who actually created the invention, not to business entities or partners. I was the sole inventor of every technology Bradford Chen Engineering had developed. Thomas had no legal rights to my inventions regardless of our business partnership. "I've contributed to these projects," Thomas insisted, becoming defensive. "I've brought in the clients, managed the business, made this firm possible. You're acting like I've done nothing when my business development has been essential to our success." I acknowledged that Thomas had handled business operations, but pointed out that business development didn't entitle him to claim inventorship of technologies he hadn't created. His contribution was management, not engineering. He'd systematically misrepresented himself as the inventor of technologies I'd developed, which constituted both professional fraud and legal fraud in patent applications. I explained that his fraudulent inventor declarations on patent applications were particularly serious legal violations. Patent law required truthful statements of inventorship under penalty of perjury. He'd committed legal fraud by falsely claiming to be inventor of my technologies. The patents could be invalidated because of his fraudulent declarations. Thomas tried several approaches as reality set in. He suggested we could correct the patent applications to properly list me as primary inventor. He proposed restructuring the partnership to give me more recognition. He offered to revise our agreements to clarify intellectual property ownership. Each suggestion was a desperate attempt to prevent the dissolution he could see coming. I told him it was too late for corrections or compromises. I'd spent 2 years documenting his theft and building exit strategy because I'd lost all trust in the partnership. I explained that I'd already secured commitments from multiple companies to work with me independently, that I had legal protection for all my inventions, and that I was launching my own firm regardless of what he proposed. "You're destroying everything we've built," Thomas said, with genuine emotion rather than business tactics. Bradford Chen Engineering has reputation, client contracts, ongoing projects. You can't just walk away and take everything with you. I told him that Bradford Chen Engineering's reputation was built entirely on technologies I'd invented, that the client relationships existed because of my technical work, and that ongoing projects were based on my engineering. I explained that he'd have to figure out what to do without the technical capabilities he'd been fraudulently claiming as his own for 2 years. I handed Thomas formal written notice of partnership dissolution, drafted by my attorney. The notice specified that I was withdrawing from Bradford Chen Engineering effective immediately, retaining all intellectual property rights to technologies I'd invented, and would be filing corrections to fraudulent patent applications. The notice also warned that any attempt to use my technologies after dissolution would result in patent infringement claims. The meeting ended with Thomas understanding he had no options. He couldn't continue using my technologies because I owned the inventions. He couldn't claim the technologies were partnership property because patent law required truthful inventorship. He couldn't maintain Bradford Chen Engineering's reputation because all its innovative work was mine. His firm would collapse. I walked out of that office for the last time feeling both relief and vindication. The invisible engineer was stepping into visibility. The stolen inventions would be properly attributed. The exploiter would face consequences. And I was launching my own firm with the technologies, client relationships, and legal protection I'd spent 2 years building. Within 2 weeks, I established Chen Engineering Solutions with laboratory and office space in Mountain View. The space was smaller than Bradford Chen's facility but felt authentic and mine. I set up engineering workstations, rapid prototyping equipment, and testing capabilities. I met with company representatives who'd committed to working with me directly. I finalized contracts for 4 major development programs. The companies I'd been cultivating relationships with during my documentation period immediately transferred their business from Bradford Chen Engineering to Chen Engineering Solutions. The aerospace company signed a contract for advanced propulsion cooling system development within days of my departure. The automotive manufacturer, once they learned I'd actually invented their thermal management system, moved their contract to my new firm. Within a month of leaving Bradford Chen, I'd secured enough contracts to make my independent firm financially viable. The engineering managers who'd thought they were hiring Thomas's technical expertise realized they'd actually been getting mine, and they followed the actual engineer rather than the business partner who'd misrepresented his role. I also filed corrections with the Patent Office for the fraudulent patent applications Thomas had submitted. I provided comprehensive evidence that I was the sole inventor, including engineering notebooks, provisional patent filings, and technical documentation proving I'd created the inventions. The Patent Office initiated correction proceedings to remove Thomas's name and properly credit my inventorship. The engineering community response was powerful and validating. Multiple engineers reached out saying they'd experienced similar credit theft in partnership or corporate settings. Professional societies invited me to speak about protecting intellectual property and preventing exploitation. The story resonated because technical credit theft was more common than most people acknowledged. Thomas Bradford's reputation collapsed completely. Once companies and industry professionals learned he'd been fraudulently claiming inventorship of my technologies, his credibility was destroyed. Bradford Chen Engineering lost every major contract within 2 months. The companies who'd thought they were contracting for Thomas's engineering expertise pulled their projects. Several clients threatened legal action against Thomas for misrepresentation, claiming they'd signed contracts based on false premises about his technical capabilities. The Patent Office initiated investigations into whether Thomas had committed fraud in his inventor declarations. His engineering credentials were questioned by professional licensing boards. Within 6 months of my departure, Bradford Chen Engineering closed completely. Thomas dissolved the LLC, unable to maintain the business without any technical capabilities or client relationships. The office was vacated, and Thomas Bradford disappeared from Silicon Valley's engineering community. Meanwhile, Chen Engineering Solutions flourished. My first year exceeded every expectation. I completed 6 major development programs, filed 8 new patent applications as sole inventor, and won an ASME Innovation Award. The professional recognition I'd been denied while Thomas stole credit came flooding in once I had proper attribution. The rocket engine cooling system I'd developed became a production technology used in commercial satellite launchers. Technical publications featured the innovation with proper inventor attribution. The technology won industry awards, with my name on every certificate and announcement. Within 3 years of leaving Bradford Chen Engineering Solutions had completed over 20 major projects and filed 30 patents. My work was featured regularly in engineering publications, always with proper attribution. I'd established reputation as one of the industry's most innovative thermal and propulsion engineers. I also began advocacy work helping other engineers protect their inventions and avoid exploitation. I developed resources about patent protection, wrote articles about preventing technical credit theft, and mentored young engineers about protecting their intellectual property. 10 years after leaving, I published a handbook on engineering intellectual property protection that became standard reference in engineering practice. The book covered patent law, documentation best practices, partnership agreements, and case studies including Thomas's fraud as a cautionary tale. My work transformed not just my career but helped hundreds of engineers protect their innovations and achieve proper recognition. The invisible engineer became a celebrated inventor and advocate. The stolen technologies were properly attributed and commercially successful. The exploiter left engineering discredited. And the profession became more aware that technical credit theft deserved serious consequences. That's the ultimate outcome when exploitation meets someone talented enough to succeed independently, methodical enough to document and plan carefully, and committed enough to transform personal justice into advocacy benefiting others.